I'm gonna give it a try and I'll report back.
Okay.
If it worked.
Oh,
For me.
Where's my button? Good morning, everybody. Yes. I do not have one. That's not one in my office. Sorry. So relativity. It all started, okay, with some thought experiments involving a car. Let's see, it was Manuel's car, wasn't it? Right? And Christian was doing the measuring and Alette was doing the riding on the front of the car. Okay? So it all started with this issue of velocity addition. Right? How do we square the measurements between two frames of reference? They measure something different, but they can agree that there's a difference because of a relative velocity. So we're coming back to that. Okay, we're coming home. We're coming back to the start. Only now we've got to deal with the problem of special relativity in the sense that the speed of light is the same for all observers. And how would you add velocities together for things that are moving at relativistic speeds? The setup is usually something like this. Typically, there's some kind of, there's three people, three parties in these problems. There's some sort of observer, typically sitting on a planet or something like that, but there's some sort of observer that is measuring the speed that one object is going and the speed that another object is going. And even though I've done them with the velocities pointing towards each other, this works for any direction as long as we're careful with our sign. But the general setup is you have an observer and you have two other objects that the observer is looking at. The observer is measuring these speeds. Oh, and by the way, this is different from the way your book does the symbols. The setup's the same, concept's the same, but books and YouTube videos and internet resources use a symbology that kind of Einstein and Lorentz developed, and it's convoluted, to say the least. When you're used to it, it's okay. But for people just starting out, I really recommend that you ignore that and follow what I'm doing. The problem is that you will see symbols like U sub x prime and U sub x and V sub x, like they use this primed notation, which again, when you're used to it, it's okay, you get what's going on. But when you're first exposed to it, it doesn't help at all. It comes out of something I'm not teaching you, which is called the Lorentz transformation, which is the mathematical underpinning of relativity. You've been doing Lorentz transformations the whole time. It's just I haven't been using the formalism of it. Right? So I'm going to continue not using the formal language of relativity in an effort to help you understand better, be able to apply better what's going on. So just realize the stuff the symbols I'm about to use are different from the way your book and anybody else on the internet might do it. Okay, so what's the setup here? V1, okay, is going to be, this is the velocity of object, and I'm writing all these out because this is important. It's the velocity of object 1 with respect to WRT, the observer. So the observer measures this velocity. Okay. V2, you want to guess what V2 is? You got this. What is it? It's the velocity of object 2. WRT, what does WRT mean? With respect to the person who's measuring the observer. Okay? And then I'm going to use V21. V sub 21, not 21, just 21. Okay? V21 is the relative velocity of object 2 with respect to object 1. So there's 3 velocities that are being observed, thought about, and that we need to grapple with in any kind of relativistic velocity addition situation. There's the speed that the first object's going according to the observer. Then there's the speed and velocity that the second object is going with respect to the observer. But then there is what object 1 would see object 2 doing. Notice I'm not writing down what object 1 sees the observer doing, because we already know that. If the observer sees object 1 moving at half the speed of light, what will object 1 see the observer moving at? Half the speed of light, right? They're all relative velocities, with respect to, relative to, okay? So we are trying to figure out, though, what the 2 objects, how they're moving, how they would see it. So the typical setup here is that you've got something like V1 is moving at 0.9 c, and V2 is moving in the opposite direction at 0.7 c. Well, if this were normal Galilean relativity, it would be what we would add those 2 relative velocities up to get the speed at which they're approaching each other. What would that be, 1.6 c? But we can't go faster than the speed of light. Again, I'm going to explain why today, okay? We can't go faster than the speed of light. So there needs to be a correction. There's something deeper going on here that has to do, because velocities are velocities, this has to do both with time dilation and length contraction happening simultaneously. Boiling that all down and putting it all together, you get this. The relative velocity as measured between the 2 objects will be V2 minus V1 divided by 1 minus the product V1, V2 over c squared. This is usually the only equation they give you. I'm going to solve this for you a slightly different way, because it can come in handy. All that you have to do is do some algebra, but it is a lot of algebra. And I'll just give this to you for free, because there's more things to worry about than doing a whole bunch of algebra in these problems. But if the problem is asking you to find, like, what does object 1 see object 2 doing, you're solving for V21. Because you know what V21 is. It's that relative speed between the 2 objects. But if the problem, say, asks you to solve for how fast is object 2 going with respect to the observer, there you go, okay? You got that already solved out for you. It just kind of depends on what they're asking for in the problem, okay? So that's the setup, the toolbox, the general idea. I want to do 2 examples specifically with numbers in them to help you move safely, okay, through the minefield that is relativistic velocity addition. So, sorry, I only have 1 example. I lied. But it's a good one because it has Star Trek references in it. Okay? So, USS Enterprise? Who flies that one? Captain Kirk or Captain Picard? Ooh. Do we need to get into a fight? This one happens to be Picard's, the USS Enterprise D. Okay? Because the Imperial Klingon ship Bortas, okay, was the flagship of Gowron in the Next Generation. Is anybody following me whatsoever? No? Yeah? I've got 2 people on my side. Okay. Right? You've got to watch Star Trek The Next Generation. It's been improved. It's got an HD version now. You don't have to live by the 4x3. But it's good. It's good science fiction. Good science fiction. Yes and no. Anyway, so we've got 2 ships that are both flying towards each other, right? So again, setup is there's some sort of observer that's watching stuff that's going on, right? So I would draw a picture, okay? And what are the three, well, who are the three players in this? Name one of the players. The Enterprise. Okay. We have to be careful. There we go. Okay? That's the Enterprise. All right? So the Enterprise is approaching what? Earth. Okay? And what do we know about the speed that Earth measures the Enterprise going? 0.6 c, right? So it's moving along at 0.6 c. And then the Klingon ship Bortas is coming from the opposite direction at a different speed. So Klingon ships look a little bit like this. Okay, so that's kind of more wrong. Anyway, the vertebrae. And it's going at 0.7 c. And again, the 0.6 and the 0.7 are measured by who? Earth. So, based on our definitions, what is V1? It could be either the Enterprise or the Bortas. I'm going to choose Enterprise first. Okay? So V1 is 0.6 c, and I'm going to put a plus sign on it. Because direction matters. What direction have I just said is positive? To the right, right? I'm saying that this is my positive direction. Okay, so that means V2 has got to be the speed of what? The Bortas, okay? But how am I going to write it down? Good. Negative 0.7 c. Direction matters. Okay. So what relative speed do they see each other approaching at? What is V21 according to the definitions we had before? It's the speed of object 2 with respect to object 1, right? It's the speed that objects 1 and 2 see each other approaching at. It'll be the same speed, right? Relative velocity is the same across frames of reference. But now we've got to calculate it out. Well, we were given an equation for that. It was V2 minus V1 all over 1 minus V1 V2 over c squared. Okay, so that's going to be negative 0.7 minus a positive 0.6, and there's c's on those things. Okay, and then I got 1 minus a minus 0.7 c times a 0.6 c all over c squared. That's a lot of c's. What happens to the c's in the denominator? Yeah, so I got a 0.7 c times a 0.6 c. And that's a number times c squared, isn't it? And then I divide by c squared. So all my c's on the denominator cancel out. The c on the top can get factored out, right? It's good. Our number, now we're just ending up with a number times c, right? Okay. So then we put this all in our calculator, and we hope and pray that our calculator doesn't lie to us, and we get negative 0.92 c. Now, the question does ask for relative speed. And so the answer here should just be a positive number, right? Why did we get a negative number on our answer, though? It's the speed, right? V21, right? The speed at which object 2 sees object 1 approaching. From the Klingon ship's point of view, right? They're moving forward and the Enterprise is coming backwards at them, right? So, but they both see 0.92 c as the speed at which they are approaching each other. This problem would have changed, say, if the Klingon ship were the other way around and we're trying to get away from Earth, you would just drop the minus sign on the 0.7 everywhere. So mind your directions, they are important, right? But it's a matter of plus or minus in getting that right. Otherwise, just make sure you kind of assign your velocities correctly and watch what they are looking for, solve for the right thing. Again, the symbology in your book is going to look different. And if you're watching any other resources, chalkboard videos, YouTube stuff, whatever, they're probably going to use different symbols. They're going to have primes in them, and instead of V's, there's going to be U's and stuff like that. They're really doing the same physics. They're just using a bunch of different symbols, and I just find that 1 and 2 are better labels for people that are getting started into this. If you really want to get into relativity, come talk to me. I'll show you the language of a Lorentz transformation. It is an elegant language and a useful one, but it's a bit much. I don't even really do it for my physics 4 students because it's relativity. Everybody's confused. All right. It's time for everything else. What have we tackled so far? We've tackled time, and we've tackled distance, right? So we got t and we got x. Now we need to talk about force, mass, energy, momentum, like all the other basic things that make up how we understand and think about the universe need to change. Need to be updated to bring them in line with relativity. And so, to do that, okay, before we get to general relativity, this is going to be a sampler. This is a party tray of the rest of relativity. I'll box the things that you need to, that are useful to use, but just as a trip through how the rest of physics gets messed up by all of this. Okay? Let me give you the party tray version of relativity going forward. Does anybody remember what momentum was? Way back in physics 2A. It was mass times velocity. It was this quantity of motion that we stuck. So the classical formation of it was mass times velocity. Sure, I'll put the vector signs down, okay? So, okay, Mr. Balogh, what's wrong here? Well, time changes, and velocities are distances per time, right? Lengths are altered by relative motion, so it should come as no surprise that momentum is also changed by relative motion. And the relativistic version of momentum is going to be gamma mv. No, I don't see it, huh? You should have immediately been offended, surprised, horrified. Something's wrong here. What's gamma? What's gamma? What are the units of gamma? There aren't any, right? It's a number, right? It's just this factor. It's like how strong is the effect, right? You got to be going pretty fast in order to see relativistic effects. And so gamma is a way of kind of like gauging how strong the effect is. And so what we're trying to say here is that momentum, you're going slow enough, it's just the same, right? 1.001 for a gamma, it's small, right? It's only going to have a problem when things start going really fast. When gamma's around like 5 or 10 or 100 or whatever, right? Okay? But how do you find gamma? How do you calculate gamma? 1 over the square root of 1 minus What? V squared over c squared? But there's already a v up there. Still don't see it, do you? What is gamma affecting? There's only two things in that statement that gamma can be operating against: the mass or the velocity. So what does gamma change? The mass or the velocity? If gamma already has a velocity in it, it can't operate against the velocity. The velocity is just velocity. It's the relative velocity. It's already in there. So the only other choice is mass. What happens to the mass of something if it moves really fast? It gets bigger. What? What happens to gamma the closer you get to the speed of light? It gets bigger. When something is not moving, it has a gamma factor of 1. For every other speed, up to and close to the speed of light, that number is getting bigger. In fact, it starts at even bigger, is more than exponential growth, the closer this v gets to that c. And so that means the faster something moves, the more massive it becomes? Yes. We've measured this. All you have to do is go to the closest hospital that has a radiation unit in it. A part of the hospital that is responsible for not only doing x-rays, but also creating the radioactive isotopes that are used in imaging. These radioactive isotopes, which we're going to talk about when we get to nuclear physics, so I'm getting a little bit ahead of myself, but in order to make these radioactive isotopes, they have to be made within the hospital, like within the same town. You can't ship these via Amazon. They won't be radioactive by the time it gets to you, okay? They're very short-lived radioactive isotopes so that the radiation exposure to the patient is very low, but you have to make them in the hospital. And the way you make them in the hospital is you take electrons and you move them really, 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 really fast in a particle accelerator close to the speed of light, like 99.9999% the speed of light, and then slam them into atoms and radioactive things come out. I'll explain all of that later. The point is, very fast electrons in the basement of most hospitals. When you measure the mass of those electrons that are moving very, very close to the speed of light, you find that their mass is big. Much bigger than it would be if the electron were standing still. This is a measurable thing. Relativity happens. So, this means that there's actually more than one kind of mass. There is technically, okay, a relativistic mass that something has. And that mass will be gamma times its rest mass, the mass it has when it's standing still. Up to this point in this class, every time that I have talked about mass, I have been talking about the rest mass. The normal everyday mass that something has. But from now on, we have to be careful. If an object is moving fast enough, it's going to have a different mass than if it were sitting still. Okay, so that's relativistic mass and momentum. I mean, you could box those if you want, but they essentially do the same thing. We're not going to actually write down force. We're going to get to energy here in a second. But let's just talk about force for just a second. Newton's second law. What does Newton's second law say? The relationship between force and acceleration, mass being the thing that controls that. So now we know mass is changed by relativistic stuff, right? We're not allowed to talk about accelerations, right? In special relativity. That's why we're going to do general relativity here in a bit, right? So we really can't talk about accelerations, so that means we really can't talk about force when it comes to special relativity. But let me just point it, and by the way, Newton's second law does not look like this relativity. Actually, it's got like A cubes and stuff. It's really weird, okay? But let me just say this, and let's answer the question as to why nothing except light can go at the speed of light. Let's hop in our spaceship and punch light drive, right? We're going to hit warp drive and we're going to speed up and get as close to the speed of light as we possibly can. In order for our spaceship to get moving in the first place, it needs force applied to it, right? Or work needs to be done, in which case energy needs to be expended, okay? So, what would the mass of our spaceship be if we were able to get it to go the speed of light? It would have infinite mass. That's because gamma is a number that goes from 1 at the smallest to infinity at the highest, right? C squared. So if, not saying can, saying if, something with mass, like our spaceship, moved at the speed of light, its mass would be infinitely large. How much force, parentheses, how much energy do you need to get an infinite mass to accelerate? Just think of it classically. If this is infinity, how much of this do you need? You need an infinite amount of force, which means you need an infinite amount of energy. What kind of universe do we live in? Do we live in a universe of infinite energy? No. The amount of energy in our universe is fixed. It's a constant. Remember conservation of energy? Right? And so, nothing with mass can ever go the speed of light because there isn't enough energy in our universe to cause that to happen. That is why light, the speed of light, is the universal speed limit. In fact, the only thing that moves at the speed of light is light that has exactly how much mass? What's the mass of a photon? 0. In other words, the only way to go the speed of light is to have 0 mass. And the only thing that has 0 mass is light. So what's the only thing in the universe that moves at the speed of light? Everything else is limited. We can get close. We can take electrons that have masses measured, what is the mass of electron? 10 to the minus 24 kilograms? 21? I don't care, it's a small number. We can push them to close to the speed of light, 99.994956 after that, right? We can get them really close to the speed of light. And their mass gets really, it really starts increasing at that point. But it starts off really small anyway, right? Okay? But even to push an electron to the speed of light would require an infinite amount of energy, and we just simply don't have an infinite amount of energy in the universe. We'll talk about how warp drive works later. Okay, so that's why we have a universal speed limit. So, Einstein set out to try to figure out what kinetic energy and things would look like, because again, something that's moving has kinetic energy, right? We can avoid the whole general relativity, right? We just stick with special relativity. So I'm not gonna, I'm not gonna bother you with the derivation. It's not that interesting. But this is what the kinetic energy happens to be. It's gamma mc squared minus mc squared, okay? This right here, okay, this is our kinetic energy. This term that's got the gamma in front of it is total energy. And then this thing over here is called the rest energy. Okay, so what's going on here? Energy, the total energy of any object is going to be a combination of its kinetic and potential energies. At any one moment, an object could have energy associated with its state, like where it is, how much energy it contains, whether, heat or anything, it's just sitting there, it's got some energy, we call that potential energy. But then it can have kinetic energy, right? The energy specifically devoted to motion, to moving. What Einstein discovered is that the kinetic energy ends up being a difference between things. And if we solve for kinetic energy on the right over there, kinetic energy can be thought of as a difference between total energy and then some other potential or leftover energy. If the total energy is all contained in potential energy, you get a kinetic energy of 0. If there's no potential energy, it means the total energy is all kinetic. But if you're sharing, there's going to be this difference, right? And so Einstein finds that the total energy that anything ever has is gamma mc squared. But if it's not moving, okay, if the kinetic energy were 0, then what would the energy be? Right? But wrong. You've seen it everywhere, haven't you? That famous equation, E equals mc squared. It's only part of the story. So let me show you. I am going to show you this, and you're going to hate it. You're not going to be required to repeat it ever, so if you want to clock out for the next 4 minutes, you're more than welcome to. But let me just show you where E equals mc squared comes from. Albert Einstein took a look at this total energy, this gamma mc squared. This is really kind of the important part, okay? And he was also taking a look at momentum, okay? And relativistic momentum. And he was doing the physicist's equivalent of basically throwing spaghetti at the wall to see what sticks, okay? Trying to figure out relationships between all of these things. And he finally hit upon the following derivation and relationship. We'll do this first. So, and again, it took Albert Einstein months to figure this out. It's going to take me about 3.5 minutes to get it all written down, okay? I'm going to square both sides of the energy equation, okay? And then I'm going to do the same thing to the momentum equation. Just going to square both sides, okay, like that. And then we're going to kind of rearrange just a little bit here. I'm going to take this mc squared thing and just figure out what that is. And then over here, this one's a little bit more squirrely, okay? Let's divide by the m squared first. And I know, you're sitting there going, well, how would I ever think? I mean, the point is, I would never think of doing it. Einstein thought of doing it, right? Okay? And so, let's see, that cancels out, and so I'm left with momentum squared and mass squared equals gamma squared v squared. Okay, right? So, doesn't look like much, okay? But I'm also now going to multiply by 1. Physicists have a real strange way of multiplying by 1 sometimes, okay? Right? But again, instead of I could cancel this from both sides and have the same thing that I started with, right? So I multiplied by 1 on both sides. Okay, all right? Why would you do that? Because what Einstein wants to do is subtract this equation from this equation. In other words, he wants to take this e squared over mc squared quantity squared minus momentum squared over m squared c squared. And if you subtract the left-hand sides of equations, you have to subtract the right-hand sides too. So you end up over here is gamma squared minus gamma squared v squared over c squared. You're like, this is getting worse. There's nothing to be done for the left-hand side. In the right-hand side, we can kind of clean that up, can't we? What can we factor out here? Gamma squared. So there's gamma squared. What was that? 1 minus v squared over... Oh. Oh. What's 1 minus v squared? Where have we heard 1 minus v squared over c squared before? It's in gamma, isn't it? But it's down inside of a square root on the bottom, isn't it? So if I do gamma squared, that would be 1 over square root, but if it's squared, square root goes away. So that's 1 minus v squared over c squared. That's what gamma squared is. And then I have a 1 minus v squared over c squared. What's the right-hand side of this equation?
1.
It's 1. I told physicists just spend all day, we're just trying to write the number 1 or 0. It's equals 1. E squared over mc squared quantity squared minus p squared over mc quantity squared, right, like that, is equal to 1? Yeah. And if you do more math, you eventually get down to e squared equals mc squared quantity squared plus momentum times c squared. Or in other words, the energy is equal to the square root. Here's the part you want to write down, you're going to want to box. PC quantity squared plus MC squared squared. That thing in the box is what every single E equals MC squared equation should look like. Because that's the equation that Einstein wrote down. He didn't box it with bold type in the journal, okay? This is it! So, it doesn't look like E equals MC squared, does it? MC squared plus MC squared squared. Where does E equals MC squared come from? Can you see it? How do we get E equals MC squared out of that? What's P? It's momentum. And how do we get something's momentum to be 0? Either the mass is 0, or, this is not light, this is just objects, right? So they're going to have mass. So the mass can't be 0. So what's the other thing we can set to 0? Velocity. So if the velocity is equal to 0, then the momentum is equal to 0. And if the momentum is equal to 0, we have the square root of mc squared squared. So what does the energy turn out to be? E equals mc squared happens when an object isn't moving. If it is moving, then we've got to go figure out what its momentum is, and we've got to add on mc, and we get the actual energy. But for an object at rest, for this bottle at rest, it has energy. It has energy equivalent to its mass times the speed of light squared. How big is the speed of light? It's big. 3 times 10 to the air is 300 million meters per second, right? And then we square it. 9 times 10 to the 16. I've lost track. We're way past Terra, aren't we? Like we're into Zeta. Big number. Times mass. Lots of energy contained in the mass of this object. 9 times 10 to the 16 times 100 grams, okay? So 1/10 of a kilogram is still 9 times 10 to the 12, 13. That's enough energy to run the entire United States for about 10 minutes. I have solved the energy crisis. No, I haven't. Why? That's the amount of energy that's in this bottle. But why can't I get it out? It's in the form of mass. Mass is equal to what? Energy divided by... What's mass? Tastes like chicken? Tastes like salt? Remember that analogy I used in 2A? Right? What's energy? Tastes like pepper? They're opposite. They're yin yang. They're not equivalent to each other, but one can be transferred from one form to another. I can find the number of joules that are wrapped up in the mass of this thing. Now, if I wanted to liberate that, and I'm not talking about like the chemical energy that's in the alcohol bonds inside of this hand sanitizer. I know how to liberate that. Do we have a flame source? No, we're not going to do that experiment. Okay? Right? I can burn the alcohol in this. Right? And get energy. That's combustion. That's playing with chemical balls. I'm talking about the mass, the electrons, the protons, the neutrons, everything that's in this bottle being converted into pure energy. The only way we really know how to do that is called an atomic bomb. And even then, they are only at most 8 to 10% efficient. Most of the mass in an atomic bomb just gets blown up and not converted into energy. We can do it in a reactor, which is similar to a bomb, only less booming. Technical term. So that's where E equals mc squared comes from. But it is actually the least interesting result. Okay, yes, it spawned a whole industry and nuclear stuff, and we're going to get to that, okay? But it's actually not the punchline here. The punchline is what? happens when you ask the other question? What's the other question? Don't see it? Okay, speed. What do you mean speed of light? It's in the equation, but we started with saying, look, what happens if this term is 0? Like, what do we get, right? If something's not moving, we get a rest energy. Great, fine. Go make some energy, go blow something, okay? Right? But what's the other question? How is this term 0? When mc squared becomes 0, what must be true? C is a constant, right? The only other thing that could make this thing 0 is if the mass were 0. So to get the mc squared term to become 0, we need a mass of 0. And what's the only thing that has a mass of 0? So if the mass is 0, then E is equal to the square root of PC squared, which means that the energy is equal to the momentum times C, or in other words, light has momentum. What's momentum? It's massive motion! Right? Mass times force. The M is there, isn't it? Is this 0? Like, does light have energy? Yeah. Wait, it's a solar panel, right? Light has energy. You take the energy, you divide it by C, you get momentum? You get kilogram meters per second? My brain is broken. How is that possible? Remember, momentum, it's that thing that's conserved, right? And when you have momentum, like, what's the classical physics thing that you just do whenever you have momentum? What do you do? Cargo boom, right? You got objects right? And you conserve. This means, if Einstein's right, this means that I can push stuff with light. I'll be right back. Somebody stole my light bulbs. Okay? What's it? Does anybody know what this is? this bottom of a lava lamp, okay? And we like it because it has a light bulb in the bottom. And it's all set up, ready for us to go. Okay, so I've got a light source. I don't need that, that's boring. Okay, and I have one of these, okay? I don't know if you can see it from where you're sitting there in the back, but this is a light bulb that has a set of like veins in the top, and it's like mounted on a propeller type thing, and one side of the propellers has white on it, and the other side has black on it. So light side, dark side. And it's sitting on a metal needle, and it's like a glass metal bearing, like there's an interface there, okay, that makes very, very little friction on that device. And it's spinning right now because I was holding it and kind of imparting a little bit of my wiggle and shake in my hands and things. But as you can see here, it's finally come to a stop, right? Okay? So at perfect equilibrium, we have light in the room, it's hitting it from all sides. Okay? I'm going to dim the lights. Grab my light source and turn it on. It's coasting, right? It's coasting right there, right? But it is slowing down a little bit as friction takes over, okay? But there's a total this is no joke. I'm not tricking, there's no magnets in the table, okay? When I shine a light on this thing, what happens? This means, it gained momentum, didn't it? And momentum must be conserved. So where did the momentum come from? I've got this light. Okay, this is a very old light that would go on the top of a movie camera, like the old homemade, the film strips from the 1960s and stuff like that. Okay, this thing is bright. Okay, yeah, okay, right. That's why I didn't point it at you. Says 650 watts. Okay, this one was 40 watts. Okay, right? So the higher the power here, right, the wattage, okay, the more momentum the photons, the particles of light are going to have. Watch what happens. Maybe. Can you see it? You see how fast it's going? Right? Okay. We imparted a lot of momentum. Right? Okay. Because of the brighter light that's there. Right? But I hope that I have experimentally proven to you that light has momentum. And that the more exciting result here is not that mass has energy, whoop-de-doo. It's that light has momentum and can push things. NASA and the European Space Agency have studied this. We have actually built solar sails and flown them in space, using nothing but the momentum pressure from the sun. An experimental payload in low Earth orbit did change its velocity, just based on the sunlight that was hitting the sun. That means we can go places around the sun without having to carry any fuel. It's slow, it takes a while, but it's constant. We are living in Star Trek. Absolutely, positively. Okay. I can't do any of the math of general relativity with you. Number one, I never took that class, okay? I'm an experimental physicist and there are some experiments to do, but they're either very fast and cheap like the one I just did for you, or they're very expensive and require many patience. And I'll talk about those experiments in a bit. So I can't do general relativity's math because I never did it. I mean, could I understand it? Maybe. There's a whole new, it involves a lot of calculus, differential equations, tensor calculus. There's a lot of stuff going on mathematically, but we can talk about it conceptually, like what it is and the implications of it and why it's so important. So that's what I want to do now. I will point out that I did fool you a little bit with this demonstration, okay? This demonstration isn't all about momentum, okay? There's heat transfer that takes place via electromagnetic radiation, which does most of the pushing of these things, but I didn't want you to go out and look it up and Mr. Balogh lied to us. I lied a little bit, but I came clean. All right, there is momentum there, it's just, it would take a lot longer for it to speed up. Okay, so what's going on with general relativity? Albert Einstein in 1905 published the special relativity, right? 2 papers. First one was ideas, second one was all the math, followed up a few months later. It would be another 10 years of work on Einstein's part to formulate the general relativity, which allows for accelerations, which takes up the entire breadth of physics. It doesn't limit it to just people moving relative to each other, but allows for changes in directions, accelerations, that sort of stuff. And so, like the special relativity, Einstein wanted to start with very simple postulates. And it turns out that there's only one postulate of general relativity, one idea, one foundational principle from which space-time emerges. And it's this. It's called the principle of equivalence. And like the postulates of special relativity, at first glance, it seems too simple. Like, well, duh. Okay? But it is far-reaching in its implications. The principle of equivalence says this. The laws of physics, the experiments that you can do, the data that you can collect cannot tell you the difference between a gravitational field and a frame of reference that is accelerating. What the heck does that mean? Let's do an experiment. I have a tennis ball, right? Okay. I am going to let go of the tennis ball. What is the tennis ball going to do? It's going to fall. Okay? Why did the tennis ball fall? Because gravity, right? What did gravity do? Pulled it down, right? Caused this mass to accelerate and pick up speed because there's a gravitational field being caused by the Earth and this ball is simply responding to the gravitational field. Okay? That's what Newton says. What Einstein says is that there is no experiment that can be done that can tell the difference between gravity pulling this ball down versus this room accelerating straight upwards at 9.8 meters per second squared. That's stupid, Mr. Balogh. Of course, this room isn't accelerating up at 9.8. All you have to do is go outside and look, right? Prove it. That's Einstein's point. Gravitational fields look exactly the same as accelerated frames of reference. We'll get to the implications of what that means here in just a second. But at the base level, this is what Einstein is trying to say. Now, of course, he did it a little bit more carefully. He would say things like, the lab that you're doing experiments in has no windows, right? So there's no external way to show, right, that your frame of reference is either on the surface of the Earth or moving through space with an acceleration of 9.8 meters per second, right? There's no experiment that can be done within the confines of your lab, your boundary conditions, that can tell the difference. And of course, Einstein understands if you look out the window of the spaceship, you can see that you're moving or something like that, right? But the point of the principle of equivalence is that how are we going to like what uniquely describes a gravitational field versus an accelerated frame of reference? So let me give you some idea. These are very simple animations of the comparison of objects moving in a gravitational field versus an accelerated frame of reference. I got 2 frames of reference here. Think of these boxes like labs, right, with no windows, and you're standing inside. If I hit play here, right, on the left, we see a box that is moving upwards, and then we see this red ball, this dot that moves across, right? Okay? And if we just concentrate on the left-hand one, we see the ball moving straight across, okay? Following Newton's first law, object in motion will stay in motion unless acted upon by an outside force, right? Okay? But the frame of reference is accelerating relative to that straight line motion. Whoops. The picture on the right looks like what? That just looks like a ball that was thrown to the horizontally, doesn't it? Okay, throw a ball horizontally, it's just going to fall, right? The picture on the right is the one that you would picture in a gravitational field. The picture on the left is the one that you would picture if you were in an accelerated frame of reference. But if you're in this accelerated frame of reference and you don't know that you're accelerating, what would you see? Look at these. The motions inside of these 2 boxes are exactly the same. Sometimes it just takes a while, but even though that ball's moving in a straight line, you see how the floor is getting closer? Right? So for somebody in this box, they would see it happening like that. Meaning that there's no way to tell between an accelerated frame of reference versus a gravitational field. Okay. Same experiment, only now we are going to have the ball move along this line. And what you want to, and we're going to set this thing in motion right here, okay? Let's see, compare and contrast what an accelerated frame of reference versus a gravitational field would look like. See if you can't convince yourself that that person in this accelerated frame of reference is seeing that. What does the ball do? Starts in their hand, goes up, hits a peak, and comes back down? Even though it moved in a straight line? From an outside observer's perspective? The person in that box cannot do an experiment that would tell the difference between what's happening on the left versus what's happening on the right. Do you think you can see what the person inside the box is going to see? The ball is going to go on that parabolic path. It's an accelerating frame of reference. It changed the direction, so what? Still accelerating, right? Okay. You cannot tell the difference between a gravitational field and an accelerated frame of reference. In the absence of any external clue right? One must conclude that gravity doesn't exist. In other words, gravity is not a unique force responsible for that motion, because it can be explained a different way. We could explain it as the ground accelerating upward to meet that ball. Gravity, as a force, may not be necessary. That's a big deal. Because, come on, we got to the moon understanding how gravity works, right? We know, like, gravity, it's here, right? But what Albert Einstein and I am trying to tell you is that fundamental force, in fact, the only fundamental force you learned in Physics 2A is gravity. What are the four fundamental forces? Gravity, electromagnetism, and then we got two more that we're going to get to, nuclear and the strong and weak nuclear forces. Those are the four fundamental forces. And now Albert Einstein is taking one away from you with this principle of equivalence. That requires extraordinary proof. So of course, Albert Einstein decided to link it to his favorite thing. And what was Albert Einstein's favorite thing? The thing that got him started on this the entire way? It was light, wasn't it? He wanted to know the nature of light. He based the special relativity on the speed of light. So, Albert Einstein said, okay, if the principle of equivalence is true, then light should be affected by gravitational fields. Let's flip this on its head, right? Light, this thing with no mass, if we can't tell the difference between a gravitational field and an accelerated frame of reference, then somebody standing with a flashlight in a box, right, that's accelerating upward, should see that beam of light deflected, right? The beam should be moving straight across, but the frame of reference is accelerating. You have to have a really big lab, long lab, or a really rapid acceleration, but to see this effect. But the idea holds true. The principle of equivalence is happening, then it doesn't matter if it's a baseball, a tennis ball, or a beam of light. They should all be affected by the illusion of gravity, the accelerated frame of reference. And so, what does Albert Einstein have to prove? What's the experiment that must be done to show the principle of equivalence is true? He has to bend light with a gravitational field. I mean, in 1910, your social media options are limited, right? Like, Twitter takes like 4 weeks to get across to Germany out into England or anywhere else, right? Like, it's like steam engines. Electricity is barely a thing. Like how? What? Where's Einstein going to get enough mass to bend light? Do some calculations. Just go. I need something the mass of the sun. Oh. I need the sun. Where's the sun? Where's the sun? You guys are not this messed up. Where's the sun? It's in the sky. What else is in the sky? Think bigger, not birds, not clouds. Space. And what's in space? Besides the sun. Other suns. called stars, right? Why are the stars not out during the day? They are. Why can't we see them? It's too bright. The sun gets in the way. So Albert Einstein needs to see the light from distant stars bent out of the way by the sun. But the sun is too bright. I need the sun in the sky, but I need the light of the sun to be shut off. What just happened last week? What happens during an eclipse? Mr. Trelawney's sitting in the back of the room, okay, waving a poster. Mr. Trelawney, you're giving an astronomy lecture on, was it April 18th?
Thursday evening, yep.
Yeah, Thursday evening. Pitch it.
So, myself and the other astro instructor,
Mr. Ragsdale.
Mr. Ragsdale, both of us will be giving a, colloquium that's pretty official sounding. We're going to talk about astronomy a little bit and the big hot topics, right? Firstly, the eclipse that we may or may not have seen. Right? We traveled to Texas out of state for totality to see the eclipse, so we'll talk about that. We'll talk about the cutting edge. That's a buzzword. I like that. With the major announcements from the James Webb Space Telescope, right? The successor of Hubble, that's in Earth orbit on the other side of our moon. We'll talk about that. And then we'll also talk about the future of human spaceflight. Right? So prospect of using the moon as a launch pad to Mars. So that's all Thursday evening, 6:30 till about, I don't know, when we feel like we're done talking. And then after that, we'll set up some telescopes to look at the moon. What phase is our moon in?
The right one.
So quarter minute?
Yeah, it's pretty close to quarter.
Yeah,
right?
it's increasing.
Yeah, so it's getting bigger, it's waxing quarter. Thursday night, it'll be a just past quarter, so it'll be prime time to see it. So here, there's a picture up there.
Yep.
Feel free to take a picture of it.
Mr. Trelawney, are you gonna have any way to take roll with that thing?
Take roll,
Yeah.
I can have paper and pencil.
Okay, do you guys want extra credit?
Yes.
I will
Let's talk.
differentiate between classes and whatnot.
But let's figure out a way, right? It's the least burden on you, but as a way for me to verify that somebody was there and I can give you guys extra credit for going.
Take a picture and send it to you.
Yeah.
No self-confirmation with you.
Yeah. That gets problematic too. Maybe I can have some questions for them to answer and they'll be based on what you're talking about.
Yeah.
Let's talk. You guys interested in, how many of you cannot go because of work? Things like that. So only two of you?
Technically, even I can't go because of work, because I'm giving an exam.
Yeah. I'll try to make it fair for everybody, but are you guys interested in that? Okay, so let's see if I can get more people there for you and have them learn something, because we're going to talk about the stuff he's talking about when we get to the end of this class. How do we do an experiment? We got to have an eclipse. So it's 1915. Albert Einstein opens the almanac, whatever, right? When's the next eclipse? And he finds one. That's going to happen in the tail end of 1915. Anybody want to tell me what happened at the tail end of 1915 to a certain archduke? A world war began. World War I. More on what happened to the scientists that set out to watch that eclipse and get Einstein's data on Thursday. See you then.